For the homeworks problems video, we're going to start with something similar to one we did in the last homework problems video here. There's three things. You're supposed to plot the values of the functions and their derivatives at these different points. So let's look at f. Oh, I thought that was f of g, but now it looks like f times g. Let's assume it's f times g. Let's just look at this one together. Okay, so f times g, we're going to want a big graph. Hopefully this is big enough. We'll see. We don't need to go very far. It only goes to x equals 3. All right, and then let's see, 1, 2, 3, 4, 5. 5 is up here. Then we need to go down to, these functions are never negative, so it's fine. So first, let's graph f times g. We'll graph it in red. Again, it only needs us to do it when x is 1, 2, or 3. So when x is 1, well, this is the point 1, 3. This is the point 1, 2. What is f times g? It's the outputs. 3 times 2 is 6. So we're at up here at 6. And now when x is 2, this is the point 2, 1. When x is 2, this is the point 2, 3. What is the value of f times g? It's just their outputs multiplied by each other. 3 times 1. This is where f times g is here. Finally, this is the point 3, 2. And this is the point 3, I don't know, 2 and 2 and, I don't know, 2 1/4. Multiply the functions, we get 4.5. These are the values of f times g. This one's a lot harder to draw a curve on. Okay? So, can we graph its derivatives? Well, what is the derivative of f times g? That's going to be f prime times g plus f times g prime. We're going to need these derivatives at all of these points, and then we'll plug them in. So when we do that, what's the derivative over here? If we look at this line, it looks like the slope of this line is about -2. You could find a different approximation, but it should be something kind of close. Over here, oh, these are the same functions as before. I could just cheat, use my answers from earlier. The derivative here, it's not cheating, you can do it too, is the slope here is 0, right? We have a horizontal tangent line. And just like I remember doing before, the slope over here is about 1. So, what about over here? What's this slope? When I look at it, slope looks like about +3. Over here, if I graph the slope, looks like about +1. And over here, if I graph the slope, looks about -2. Oh, I'm using F's. I should be using G's. All right, these are G's over here. Great. So we can find the derivative at each point. When x is equal to 1, what's our derivative? F prime of 1 is -2. G of 1, the function value of g, the original function, is 2. Plus f at 1, the original function at 1 was 3, times g prime at 1, which is also 3. Write this all out, you get -4 plus 9. is positive 5. The derivative of fg is right there. When x is equal to 2, we got something very similar. F prime at 2 is 0. G of 2 is positive 3. Plus f of 2, positive 1, times g prime of 2 is also positive 1. You're going to get a value of positive 1. Where again, this is the derivative of f times g. Finally, when x is equal to 3, f prime of 3 is equal to 1. G of 3 is about 2 1/4. That's 9/4. F of 3 is 2. And G prime of 3 is about -2. Type that all in. That's a little harder. You're going to get 9/4 minus 4. 4 is 16/4. We're going to say about -7/4 or -2 1/4. No. -1 3/4. So -1 3/4 will be about right there. So red is the function, blue is its derivative. The actual shape of the function is more complicated here. All right. Let me know if you have any questions about this. We got some more ones. Find the derivative of this function. So this is one of the messier functions. We need the product rule. We'll take the derivative of the first times the original second plus the first function times the derivative of the second function. And again, this is what I meant in the messy problems video, where if you got something really messy, just write it all out and do it all in steps. Now, this first thing is pretty easy. The derivative of x is just 1 from the power rule. 1 times anything is that anything. We just have 3x plus 7 raised to the 5th. Oh, but now we really need to go off to the side and use the chain rule. Okay. So here's our inside function, u. All right, so we have, let's go off to the side. Y is something, u is 3x plus 7. Y is what's happening to u. It's u to the 5th. So dy dx is dy du, du dx. The derivative of y with respect to u is 5u to the 4th. Derivative of u with respect to x, this is a line. Its slope is 3. We get 15 times u, which is 3x plus 7, to the 4th. So that's what this derivative is over here. 15 times all that. And again, the other way you can think about this derivative is take the derivative of the outside function. 5 comes down in front. Subtract an exponent. Now it's an exponent of 4. Leave the inside the same. Multiply by the derivative of the inside, which is 3. That's where the 15 comes from, the 3 times the 5. And this is a perfectly good answer, but we can simplify a little bit by factoring. Right? We have a 3x plus 7 raised to the 4th power in both of them. When we take it out, the first one is left with 1 3x plus 7. There were 5 being multiplied. We took out 4. There's 1 left. The second function's left with a 15x. And then we can simplify to get 3x plus 7 to the 4th times, combine like terms, 18x plus 7. No more combining, no more factoring. That's our final answer. There it is. All right, I don't think I'm going to do this entire problem, but I do want to talk through parts of it. A manufacturer has determined that an employee with D days of production experience will be able to produce approximately this many items per day. So first, it wants us to graph it. We can graph it on Desmos and see the productivity depending on how much experience they have. Okay. So if we type this function in, productivity is 3 plus 15 times 1 minus e raised to the negative 0.2d, like so. And what does this look like? Well, let's look from, I don't know, 0 to 30 days or something. And then production up to 50. Oh, 50 is too much. Maybe 25. And again, you can see that early on, your productivity increases really fast. When you don't know anything, you don't make very much, but you get better pretty quickly. And then once you've been doing it for long enough, you're really not getting that much better. Okay, you still improve a little bit, but which kind of makes sense for how you might think about it. All right, so we graphed it. Approximately how many items will a beginning employee be able to produce each day? Well, beginning employee hasn't worked there at all. D is equal to 0. It can produce P of D. It can produce 3 items. D equals 0. P of 0 equals 3. Our answer is 3 items in a day. B says, how many items will an experienced employee be able to produce each day? What is an experienced employee? It doesn't tell us. But notice what's happening to this graph. It's getting really close to 18. So if an employee has been doing this for a long time, they can probably get close to 18. About 18 items per day. And again, it's no surprise that the experienced person will be able to manufacture many more items. C, what's the marginal production rate? You might see, Jason, we haven't talked about marginal production rate. We've talked about marginal cost, marginal revenue, marginal profits. Well, what was marginal cost? That was the derivative of the cost function. Marginal production rate will just be the derivative of the production rate. All right. So what is the marginal production rate of an employee with 5 days of experience? That's going to be P prime of 5. We need to find P prime, then we'll plug in 5, then we'll interpret our answer. Okay. So P prime of D, the derivative of P with respect to D, well, we'll have to take the derivative of this function. Well, that's the derivative with respect to D of 3. We can use the constant multiple rule to bring out the 15. Derivative with respect to D. Oh. I hate it when D is the variable. You get some very silly looking stuff. D. Yeah, technically it's correct though. The derivative with respect to D of 1 minus e to the negative 0.2d. Derivative of a constant function, 0. This 15 will hang out. And then again, the derivative of this constant function is 0. We really need to just take the derivative of e to the negative 0.2d, like so. So that's going to be the chain rule. Right? This is going to be our u. This is our inside function. Oh, I wrote d again, or x again. It's d. So it says we take the derivative of the outside function, and the derivative of an exponential function is itself. And we multiply by the derivative of the inside function. The inside function is a line. The derivative is its slope. You can do this out the long way as well with the Leibniz notation. I would recommend it. And now we just simplify. Negative times a negative is a positive. 0.2 is 1/5. So 0.2 times 5 is, times 15 is just 3. It's a fifth of 15. We get this. This is our slope function. Oh, we can see this graphically. We're not done yet. But we can see this graphically. Slope function being 3 times e raised to the negative 0.2d should, oh, it doesn't like that I called it p prime. The slope is biggest at the start. White, the value of white is the slope of blue. The value of white is the biggest at the start. The slope of blue is the biggest at the start. Blue flattens out. The slope gets close to 0. The value of the slope function gets close to 0. All right, we need p prime of 5, though. The marginal production rate. And that'll be 3 times e to the negative 0.2 times 5. 3 times e to the negative 1. We'll need a calculator to approximate that. It's 3 over e. About 1.10. What does this mean? And what are the units? Remember, the units of a derivative are just the units of the function divided by the units of the input. What's the unit of the function? Items per day. And we divide that by the units of the input, which are days. So it's going to be item per day, which is a little weird. But think about what this original function talks about. And again, we're looking at the slope right here after 5 days. After 5 days, they can produce about 12.5 items in a day. How is that changing? Derivative is rate of change. Derivative is how is that changing? They're doing about 12.5 items every day this far into their work. How is that changing? Well, it's increasing by about a little more than 1 item per day every day. So every day, their daily productivity goes up by about 1, is what we have right here. Okay, so a couple of ways that you can interpret that. I'll give you 2 ways you can interpret this. Is after 5 days, an employee's productivity is growing by about 1.10 items per day each day. Okay. Another way of thinking about it is on the 6th day, an employee will produce about 1.1 more items than on their 5th day. 2 ways of thinking about marginal productivity, very closely related to marginal cost. Okay, it's how is the productivity changing over time? All right, I will accept either one. Either is good. Okay. Let me know if you have any questions. That's it for this section. I know it was a long one. Most textbooks that I have used split this up into about 5 sections. So we did 5 in 1. Thank you to the textbook. But yeah, we're not going as in depth on some of these. So we kind of put it all together so we can spend more time on the applications. Don't worry if derivatives are still hard for you. We're going to be reviewing and practicing derivatives for the rest of the chapter. And even in chapter 3, when we get into integrals, we're really going to still be doing derivatives there, but I don't want to spoil that for you. You got that to look forward to, chapter 3. Anyway, take it easy. Good luck and good night. Bye-bye.